This is Lecture 18 in the Fiber Optic Association series on fiber optics. This lecture is going to be on OTDRs, but specifically how to set up your OTDR to make measurements properly. As we mentioned in Lecture 17, OTDRs are very valuable instruments for fiber optic testing. They're convenient because they work from one end of the cable and they create a snapshot of the cable. You use that snapshot, or what we call the trace, to analyze the cable plant as you're testing it, and you also save it for later analysis in case you need to do troubleshooting. But the secret to success in using an OTDR is before you make any tests, set the OTDR up correctly for the cable plant you're testing. Most of the questions we get at the FOA about fiber optic testing deal with somebody having problems with an OTDR. And generally the one thing that they don't do properly is set up the OTDR before they try to use it to test their cable plant. Too often they depend on just pushing a button and depending on auto test, and that's a recipe for disaster. You need to know something about the cable plant you're testing. You need to know how to operate and configure your OTDR. If you don't do that, it may result in a disaster, and you'll end up calling us and we'll add you to our list of OTDR problems. In order to get good data from an OTDR, you need to set a number of measurement parameters. The range, which should be set to twice the cable length, the wavelength to match the wavelength of the system you're testing, the pulse width, which determines how far the OTDR can see in the distance and how well it can resolve closer, the number of times you average the signal, which reduces the noise, and the NVP, nominal velocity of propagation or index of refraction, which is the calibration for the distance measurement on the OTDR. Let's look at all of these in detail. The first parameter you need to set is the range. The range of the OTDR needs to be obviously longer than the cable plant you're testing, and generally for setup we suggest about twice that length. If you set it too short, you'll get traces that look like the green trace and the red trace here on some OTDRs because they don't have enough time on that range you've set to analyze the end of the cable plant. If you get anything that doesn't look right or looks like the green or red trace, you've set the range too short. Better to have it too long than too short, at least to begin with, because you can always change it for another trace. The second parameter you should set is the wavelength for a test. Here we're comparing two traces taken of a multi-mode cable plant. The bottom or green trace is at 850 nanometers and the top or blue trace is at 1300 nanometers. And you can see how the slope of the fiber curve shows you the attenuation coefficient of the fiber. About 3 dB per kilometer on the green curve at 850 and about 1 dB per kilometer on the blue curve at 1300. So the next thing you need to remember is to set your OTDR for the right wavelength for your test. One of the most important parameters is to set the pulse width. The pulse width allows you to determine how much power is in your test pulse, and therefore how far out the cable you can see. Now look at these three traces. The blue trace at the bottom, which is very noisy at the end, was taken with a very short pulse, which doesn't have much power in it, and it leads to higher signal-to-noise ratios at the end. The red trace is a wider pulse with a little more power, and it's not as noisy toward the end of the trace. The green curve is a very, very wide pulse, and it's much less noisy. But as we'll see in a second, it affects our resolution up close. Two more traces showing the effects of pulse width. In the trace to the left, you can see how the higher power in the green curve at the top causes the OTDR to saturate. Whenever you see a reflectance pulse that's flat at the top, it's saturated. and therefore we've got more power than we need in order to make measurements. The 3 at the right shows the effect of resolution. As we go to wider and wider pulses, we cannot see as much detail around an event. The bottom event has a very sharp reflectance pulse. The one in the middle has a broader one, and the one at the top we can hardly see at all. If we're trying to see close details, like patch cords or any kind of events close to each other, we need to use the shortest possible pulse from the OTDR. One way to reduce the noise in our traces is to use a wider pulse, but then we lose resolution. Here's another way. We can average the signal more. What we do is we make multiple measurements, and the computer in the OTDR averages it to reduce the noise. If you look at these 2 traces, the green trace is the noise from one measurement, and the blue trace is the noise taken from 1,000 measurements and averaged. So we use averaging to get better signal-to-noise ratio with a narrower pulse for better resolution. The downside of averaging is it takes us longer to make a measurement. So it might take us 2 minutes instead of 30 seconds to get the trace, but we get a cleaner trace that's easier to analyze. OTDRs use the nominal velocity of propagation, NVP, or index of refraction, in order to calculate the length of the fiber. The length equals the time that the OTDR measures times the velocity of light in the fiber, which is determined by the NVP, or index of refraction. Sometimes we know this and sometimes we don't. Sometimes we just have to set an average because we're looking at a long cable plant that has numerous fibers spliced together that may be different. So this induces an error that we sometimes can compensate for and sometimes we can't. But it also affects the length measurement, and we need to understand it as well as possible. If you don't know particularly what it is, set the value to an average. If you don't set up your OTDR correctly, you may end up with a problem like this. This is a trace that an end user sent us to analyze because they didn't quite understand what it was saying. It was taken by an installer who simply put the OTDR on the cables and hit the auto test button. If you look at the lower trace at 1300 nanometers on a multi-mode cable, the reflective events all saturate the OTDR, and the recovery isn't fast enough that you can actually see the cable at all. Yet the OTDR on auto test gave each of those a pass, and the customer could not understand why. Take a little bit of time, understand how your OTDR works, and set it up correctly so your customers don't end up sending us traces like this to analyze. Be sure to view the other FOA lectures on OTDRs on our YouTube channel, as well as the other lectures on testing, fiber optic installation, design, and components. And also go to the FOA website for our online reference guide to fiber optics, where you'll find much more detailed information. We're the Fiber Optic Association, the professional society of fiber optics. We hope you enjoy our YouTube videos.